This is the third installment of the crash course in Regents Chemistry, and this video will be reviewing bonding and chemical naming. Now, on the Regents, the New York State Chemistry Regents, they actually slip in a little bit of stoichiometry and mole theory in this part of the course. I'm trying to give the series in order of the questions as they appear in the part A of the test. In any case, I'm going to go do bonding and chemical naming because it fits nicely with the periodic table. Then my next chapter course or next crash course installment will do a little bit of mole theory as you would see it on the Regents. Okay, so let's get started. So we're talking about bonding, and bonding fits nicely with the periodic table because we just left off talking about the differences of atoms. As we go across the periodic table, the atoms get smaller. The nuclear charge, the charge in the nucleus increases. So something like lithium, who has 3 protons compared to fluorine, who has 9, okay, you can clearly see that fluorine has a greater attraction for electrons because it can pull in those electrons in closer because it's greater nuclear charge in that row. We call that attraction electronegativity. And electronegativity is a big piece, okay, of this crash course because this is a word that we use to identify types of covalent bonds. Okay, now we'll talk about that attraction for electrons a little bit later in terms of covalent bonds, but we're going to start with ionic compounds first, or ionic bonding first. Now, as I've told you, the larger atoms are to the left and downward, because as you go down, okay, the atoms actually get bigger. Okay, and essentially we have this pattern of radii as we go across the nucleus. As you can see, actually that's not a really good one, and you get the idea. You get smaller, but as you go across, you do get bigger. Okay? Alright, so my art skills are failing me there, but you get the idea. So what we're talking about here is the atoms in the upper right-hand corner of the periodic table, as we've already talked about, are the smaller atoms. They're the nonmetals. And they tend to gain electrons or get reduced, as we talked about. The metals, okay, are the large atoms. They tend to lose their electrons, as we've already talked about, because, well, they hold their electrons loosely, because those electrons are, again, not attracted to the nucleus as well as these smaller atoms. It really comes down to how big or small you are. The smaller the atom, that means your attraction or electronegativity has to be greater. So we've defined the periodic table as nonmetals versus metals. Let's go there for a second. So here we are. The separatory, of course, are our metalloids that we've already talked about. The boron, the silicon, the arsenic, tellurium, antimony, and germanium. These guys separate, okay, the nonmetals up to the right, nonmetals, with all the rest of the atoms that are below the staircase, excluding hydrogen, okay, and these, of course, are our metals. Now, the first type of bonding is going to happen between the metals and the nonmetals. Well, clearly, if I'm good at gaining electrons because I become negatively charged, and these metals always become positive, it's a good idea to figure out how these atoms would bond to each other. If I've got, okay, sodium, who's got 1 valence electron, and I've got chlorine, who's got 7. Okay, you might think they could share to get the 8, but chlorine, being so much more electronegative than sodium, actually takes the sodium's electron and it makes an ion. Sodium loses the electron and becomes an ion. It's important you understand that chlorine, being 2-8-7, by gaining an electron becomes as stable as argon, and sodium 2-8-1 by losing electron because it becomes as stable as neon. So these guys are driven by becoming stable. Let's go back. So there's 2 factors here. Number 1, chlorine wants to become stable. See, bonding, and it's very important you understand this, bonding is a scenario where atoms achieve stability. It's very important now. Stability means low energy. So when atoms bond, they're going to a lower energy state, and that's why you have to know when bonds are being formed, when sodium plus chlorine gas, okay, come together, okay, they make sodium chloride, and it is going to be exothermic because anytime we form new bonds, energy is released. Has to be. Why? Because we're creating a stable state. What is that stable state? Well, chlorine, when it gains this electron, okay, becomes chlorine -1. And as I just mentioned, it becomes 2-8-8, which is the same configuration as argon. Sodium, okay, by losing that valence, becomes 2-8, and it has the same configuration as neon, and it would be +1. And this positive ion would attract this negative ion. And we would create a bond which is a stable scenario. Now, in truth, it got stable by losing and gaining an electron to achieve a noble gas configuration, but nonetheless, it created a bond and a stable scenario. Energy had to be released. So you have to know when bonds are formed, energy is always released. And the opposite is also true. If these are a low energy state, if things are already bonded, already using each other to achieve a noble gas configuration, if you're going to break a stable state, you'd have to add energy. So we know the forward reaction is exothermic, creating a bond always releases energy, and we know the reverse has to be endothermic, which makes sense. To break something or to break a low energy state, you need energy. Okay, and that's a very important core concept. Now back to this right here. All right, let's get rid of some stuff that's in my way here. Now, sodium and chlorine. Now, why is there this movement of electrons, which is an important thing to understand? It's called the transfer. Why was there a transfer to make ions? Well, there was because I dealt with atoms that were small, that had high attraction, which we called, guess what, electronegativity. I'm just going to abbreviate it as EN. Okay, and with what? Large atoms, large atomic radii, that got low attraction, electronegativity. So this is really the strength for that electron. And because nonmetals are highly attracted for electrons, the difference in this attraction or electronegativity is high. Large atoms have a low electronegativity, small atoms high for reasons we've explained. So when you put them together, the one that's stronger for electrons will take the electron and cause a transfer. We've created ions. This is an example of ionic bonding. Now, in the easiest form, it's when a metal, a large atom, and a small atom, okay, are involved. Why? Because the difference in electronegativity will be high so that there's a transfer of electrons. I always give the very silly analogy of my son and I, my 3-year-old, okay, that's me, of course, all that hair, and my little son, who is 3 years old, okay, he has hair too, all right, and we have a tug of war. All right, before I leave every day, I have a tug of war with my son, and I am able to yank the rope away from my son every morning because I'm acting as the non-metal. And of course, I pull it out of his hands and I say, "Who's your daddy?" No, I don't say that, but what I do say is this is a good analogy to show that I was able to pull this electron or this rope, which represents electron, away from my son. This is him crying, okay? No, I put gloves on him. And he is the metal. He lost the electron, and I was able to pull it away. Why was that scenario possible? Because the difference in my strength was higher than his strength. That's what happens here. The difference in the strength for electrons, called electronegativity, is higher for the nonmetal. So much higher, we are able to have a transfer. Now, there's a general rule, and it's a 1.7 rule. It doesn't always work, but it's a general rule. If the difference in electronegativity is greater than 1.7, you're saying there's a great difference in strength, we have something called an ionic bond. You've just made ions, and we make ions by losing or gaining electrons. Let's look up. Let's go find where electronegativities are found. So I am at table S of your periodic table, and this lists of all things, among other things, the name, the symbol. Sometimes, hey, how do I know the symbol in a name? They give that in table S. First ionization energy, electronegativity, the melting point, boiling point, density, and the size of the atom called atomic radius. Now, what I'm after is electronegativity. And if I look for, okay, chlorine, I find the electronegativity is pretty high, 3.2. Sodium is 0.9. So clearly there's a huge difference in electronegativity here. Why? Nonmetals are smaller. They attract their electrons much, much better than metals who barely attract them. That's why they lose them. So you take your 3.2 and minus your 0.9, and what you get is 2.3. This is a large difference, way above 1.7, so there's a big difference in strength, like my son and myself, would cause a transfer of that rope or the electron, thus making ions. So a huge difference in electronegativity, there's going to be a transfer, and there's always going to be a huge difference between the nonmetals and the metals. Therefore, ionic bonding is essentially between a metal and a nonmetal. Now, as an aside, something I didn't cover in another series, when sodium loses an electron, okay, when a sodium atom becomes a sodium ion, when it loses an electron, does it look familiar to you? Yeah, it looks like oxidation, right? So when it loses an electron, okay, what happens to the size of the radius? Okay, well, if you lose an electron, sodium, if you look on the periodic table, has 11 protons. And a sodium ion, because it's still Na, is still 11 protons. So if you've got 11 protons, okay, and you've got 11 electrons, because this is an atom, it's neutral, standalone element, here you've got what? 11 protons, but you lost an electron, 10 electrons, so now you're plus 1. If the protons outnumber electrons, guess what? The ion gets smaller than the atom. All right, so the atom is bigger than the ion. Okay, now if you don't like that, if you lose weight, what happens? You get smaller. You lose electrons, you get smaller. And what happens to chlorine? Okay, well, if I get rid of this area, okay, chlorine, when it becomes Cl negative, it did so by gaining electrons. Looks like reduction to me. So if you look on chlorine on the periodic table to save some time, chlorine is atomic number 17. 17 protons here, 17 protons here, but this has 17 electrons, that's why it's 0. This has, well, one more electron, 18 electrons. So this has one more electron than normal, and electrons outnumber the protons, so the electrons are able to move farther away from the nucleus and become a bigger radii. So what happens here is the ion becomes bigger than the atom when you become negative. Or if you gain weight, you get bigger. You gain electrons, you get bigger. Just a little side note. And they'll talk about atomic versus ionic radius. Okay, so now I know I said ionic bonding is metal and nonmetal because of the difference in electronegativity that leads to the transfer of electrons that makes the ions that attract each other. But in truth, I'm not telling you the whole story. In truth, we have 3 other pairings that give us these ionic bondings where something positive ion is attracting something negative. Sometimes you'll hear the word cation to anion. But basically ionic bonding is just positives attracting negatives. Okay, now metal nonmetal, classic case, KCl or NaF, sodium fluoride. Okay, now we name binary compounds by adding the IDE. Binary means just 2 different capitals, 2 different elements. This is sodium fluoride, potassium chloride. Okay, and these, of course, are an example of ionic compounds. The classic case that the Regents love to talk about, but there are other cases that pop up. Metal and polyatomic ion, because really ionic bonding is positive attracting negatives. Now, we could have potassium. We can also have a cluster of atoms that have a charge called polyatomic ions listed in table E. Let's go there. Here is table E. which gives me the polyatomic ions, the selected ones, and these clusters of nonmetals have charges. We'll draw those. Okay, I'll give an example why they work in a second, but these clusters will attract, okay, other polyatomic ions or nonmetals. So if I pick, let's say, a very classic one, nitrate, NO3-. Let's talk about that one for a second. So nitrate's what I'm going to talk about. So right from table E, I've got the nitrate, NO3. It's a cluster of nonmetals. When it bonds, it needs an electron from the environment to work. So this whole cluster is -1. Potassium is +1. So it's a great combination. It's ionic because I've got two different charges in here. But polyatomic ions, because they're nonmetals bonding to nonmetals, they have to actually share electrons because nonmetals, if you remember, have a high electronegativity. So if I start with the valence electrons, 1, 2, 3, 4, and 5, and then I add oxygen's valence electrons, they're going to have to share. This is covalent bonding. The reason I'm bringing it up now is because, well, I need to explain this in ionic bonding. So if you see what I'm doing here, I'm putting out all the valence. Nitrogen needs to have 8 to feel stable. See, in ionic bonding, we lose or gain electrons to get that stable octet. These guys are forced to share because these are two different nonmetals that are both high, both strong. Back to the analogy, me and my evil twin Mongo, okay, are going to have a tug of war. He is about as strong as I am. Okay, I have more hair. If you can imagine that. Now, when we have a tug of war, nobody wins because they're both the same strength. So we're forced to share. And that's what's happening here in covalent bonding. Now, the way I'm bringing this up now, because in this case, we know nitrogen needs to have 8 electrons. It's 2-5. It needs to have 3 more to be as stable as neon. Neon is 2-8. That's the octet rule that you heard about. So if you think about this, 1, 2, 3, 4, 5, well, this oxygen has 8, this oxygen has 8. Okay, well, here's what I'm going to try to do. If I don't have enough, I always add a double bond. And I lose an O there. Okay. Let's add the O back. I'm sorry, put the pair there. I'm going to add a double bond. And that gives me 2, 4, 6. So 1, 2, 3, 4, 5, 6, 7. This oxygen feels like it has 8. This oxygen feels like it has 8. This oxygen has 7, and nitrogen needs 7. We need 1 more electron, okay? And we get it from the environment some way, maybe from a metal, like K had 1 valence electron. Because it gives it up, it took it. And now this entire cluster, okay, is now -1 because it gained an electron. This is +1, and the ionic bond is in between them. So we should have learned that when you have a polyatomic ion, you have both ionic and covalent bonds right there. So anytime they ask you which of the following has a covalent and an ionic, you're looking for a polyatomic ion in a salt or a crystal. Now, I didn't mention the word, but ionic bond makes salt compounds. Salts are things ionically bonded. Okay, so let's get this out of the way here. So KNO3 is an ionic compound. Why? That cluster of nonmetals that needed something, okay, needed an electron is -1. It's attracted to this positive one that lost it. And there is your ionic bond. Now we know in between the nonmetals, they're sharing. They're forced to share, and it's called covalent. But it's still an ionic compound or a salt. By the way, its name is called saltpeter. It's its common name, a major component of black powder or gunpowder. So potassium nitrate, metal and polyatomic ion. I can have some other ones that are listed. We can do, hey, lithium, which is +1, phosphate. Phosphate is PO4 -3. And notice I wrote 3 because I need that. Now these are ternary compounds. Their naming has to be done with the metal in front and the name of the polyatomic ion. So this is potassium nitrate, lithium phosphate. Notice I don't say trilithium. These guys had to have the IDE at the end because they were binary. So when you name something with a polyatomic ion, it's the metal in front plus the polyatomic ion. But these are still ionic compounds because you have positives attracting negatives. Okay, another scenario is a polyatomic ion and a nonmetal. Some polyatomics are positive. All right, so the ammonium atom, or ion, this guy right here is a cluster of nonmetals that's positive. Well, if it's positive, it can attract negatives. And between the positive and negative, you guessed it, you made an ionic compound or a salt. So this guy, let's do ammonium nitrate. The name of it's very simple. The name of the polyatomic ion, there's no metal here, the name of this polyatomic ion. It's an ionic compound because this is a positive ion attracting a negative. That's simple. Ammonium nitrate. Now, another example could be, let's say I had a phosphate. Okay, well, if I have ammonium, which is +1, and I've got a phosphate, which is -3, you've guessed it, the naming or the number of ions that we're dealing with here have to equal 0. So I need 3 ammoniums. So, oops, take away the positive. I'm trying to. So this is PO4, this is NH4, and let me just get rid of this. Now, you're going to need 3 of these positive ones to balance off. This is ammonium phosphate. Okay, that's simple. Now it looks like I read for the wrong line here. This is the polyatomic ion, and the polyatomic ion and nonmetal would be like something like ammonium chloride. Notice I end in IDE, chloride, because there's only one chlorine like I had here. Okay, even though it's more than one, okay, we had chloride there. So these are all of your scenarios for ionic compounds. Now, what makes these compounds ionic is, of course, the charges attracting themselves. Now, these charges are very, very strong. Because they're so strong, ionic compounds have high melting points. But they also make something called crystal lattices. They all are solids unless you heat them with enough energy. Now, of course, I'm putting a positive here. This would have to be a negative ion attracting a positive. And we would build our crystal in 3 dimensions going outwards. Okay? And because these salts or ionic compounds are not molecules, a molecule is when you have a unique arrangement that always stays the same. Okay? These do not make molecules. They make crystals that repeat over and over again. So a chemical formula of sodium fluoride is NaF, and we say this formula is empirical. Why is it empirical? Because it's the lowest ratio. Lowest ratio. Why? Well, because if I've got a salt, what I have is so many of these ions, it would depend on the size of the salt, the formula. You would never have a salt with Na 2 billion and some numbers and then an F 2 billion. We know it's a 1-to-1. It has to be a 1-to-1 for the whole thing to equal 0. So we show the lowest ratio always. All salts are given an empirical formula. Okay? And that's why we call it empirical formula. Okay? Now, this lowest ratio is important to understand because it's due to the ionic compounds acting as a crystal, and because they live as crystals unless they are dissolved in water or heated. Okay, they have unique properties. They have high melting points. Whoa, what's happening here? We have high melting points. Let's just put them over here. Let's get some room here. Okay, so because of this crystal structure, they have tremendous properties. Okay, they include, again, 1, high melting points. Takes a lot of energy. Melting points, I can do this. A lot of energy to separate them. Okay, they tend to be soluble. Why are they soluble in water? Because water has a positive and negative end, and they have this. Okay, so they're usually very soluble. 2, they have high melting points, high boiling points because of the attractive forces. Okay, and this is the big one. They are electrolytes. Put a Y in there. Electrolytes. Why? Because when they are dissolved, in water, aqueous, they have free ions, or when they're liquefied. So these things, when heated enough, if they become a liquid, or if they're dissolved in water, they have free ions and can conduct electricity. Solid, and we'll change this, never. This pops up on every test. Ionic compounds cannot conduct because they have these ions stuck in a crystal. They're not able to move when they're a solid. So they're only able to conduct when the ions are free to move as a liquid or aqueous. Okay, these are important visuals. Okay, here's again a sodium chloride crystal rotating, and you can notice there's one red to one white molecule, I should say ion, because these don't make molecules. And you may guess, well, which one is the red one, which one's the white one? Notice again, it's a 1-to-1 ratio of the white to red ions. And of course, we'd write this could be the chemical formula of, let's say, KCl or NaCl. Okay, so it's important that you understand that these things make crystal lattices. And of course, the one last piece of naming that I did forget, all right, I'm sorry, so let's start with who was the red and white one again. The smaller ion, okay, is the one that lost electrons, so this would be the metal if it was potassium or sodium in sodium chloride. And the larger ion, the one that gained electrons, the non-metal. Okay, one little piece to naming here is that if I have these polyatomic ions and I'm dealing with a, let's say in this case, a metal, okay, in front that has more than one choice, then I need to use the stock system or that Roman numeral system. So in the examples I gave you, potassium chloride, potassium nitrate, lithium phosphate, these chemicals only have one choice as far as their charges. So if I had something along the lines of, let's say, lead sulfate. Now I can't say lead sulfate because lead makes two different types of sulfates. Okay, here is one example and here is the other example. Lead, as I'm going to show you in a second, has two different oxidation states. So as you can see, lead can become +2 or +4. So these elements that have multiple positive states, we need to describe which one we're dealing with. Is it lead using a +2 or is it lead using the +4? Which lead am I using? I have to tell me that. So we use a stock system to denote that. If I'm lead using that is the +2 oxidation state, we say it's lead Roman numeral 2. Not for the second choice, but for the actual positive value. If it's lead that's using the +4, it's Roman numeral 4. For the other choices that I had listed, okay, all the way over to the other side of the periodic table, group 1 and group 2 ions only have one choice, so there's no need to tell me a Roman numeral 1 or 2 there. Only when you have multiples like titanium or vanadium. Okay, well, given these two examples here, sulfate we know is -2, that cluster in table E, so lead has to be +2 to make this equal to 0 as all salts are. So we would have again, a salt, a crystal lattice, a 1-to-1 ratio, okay, with our ions, but this would be called lead Roman numeral 2, okay, sulfate. Now because this sulfate's still -2 and there's two of them, this is a -4 overall. So this has to be a +4 here. And each lead is +4 individually because there's only one lead. So this one would be lead Roman numeral 4 sulfate. Okay, let's move on to the next form of. So covalent is our next form of bonding, major bonding that we dealt with. We just talked about ionic solids or ionic bonding at length, and now we're going to talk about covalent bonding. Whereas ionic had a transfer of electrons because the difference in electronegativity was high, covalent are forced to share, as I've already alluded to. Case in point, let's take hydrogen and chlorine. Okay, their electronegativities are 3.2, okay, and 2.2. And if you didn't know that, if you wanted to get those values, you can go to reference table S and look them up. So these are similar, okay, in electronegativity, whereas the ones we had in ionic bonding were not similar. There's a big difference in electronegativity. So we're going to share here. Now, if you were to subtract these, 3.2, 2.2, you'd get electronegativity, or a change in electronegativity, equal to 1.0, okay? Where the general rule was the change in electronegativity is what? Greater than 1.7 or equal to, we say it's ionic in nature, meaning the difference is so great there's a transfer. So anything less than 1.7, okay, in this case covalent, you have similar electronegativities that can share. All right, now I want to understand something here. There's a spectrum here. When there's a change in electronegativity, let's just draw a little graph here. When it's 0, okay, and then when it's 1.7, and then of course greater than that. So when it's greater than 1.7, and again, these are general rules. It doesn't always fit this, but we do this, okay, to talk about the general rules. So anything greater than 1.7 generally is going to be ionic. The difference is so great, there has to be a transfer. But when the electronegativities are similar, and that's from 0 to 1.7, and again, this is the difference in electronegativity, okay, we've got covalent bonds, which means there is sharing. These guys aren't strong enough to pull electrons from each other. Now, if the electronegativity difference is zero, and I don't know why everything's going crazy on me, okay, but when it's equal to 0, we like to say that this is going to be nonpolar bonds. Now, why nonpolar? Because they must be sharing equally. Case in point, let's look at hydrogen. It has one valence electron. Another hydrogen has one valence electron. And guess what? They're sharing equally. Now, I didn't draw this very well, but these electrons are being shared right down the middle because both of these have the same electronegativity. And by sharing, they both feel like they have the magic number, which is their noble gas configuration. Helium, okay, has 2 electrons. By sharing one each, they both feel like they both become as stable as their helium counterpart in the second energy level. Okay, if you look at another compound, let's look at fluorine. Okay, fluorine also has, well, it's also going to be nonpolar, but it has 7 valence electrons. And another fluorine also has 7, and they're going to share their electrons, okay, to become stable. And by sharing, okay, this fluorine feels like it has 8, and this fluorine feels like it has 8. They were both 2-7. By sharing one each, they both feel like they're 2-8, which is the noble gas configuration of neon. Okay? So instead of losing or gaining electrons to get stable, they're sharing. And the reason why they're sharing is because they have to, because they're not strong enough to do so. So it's very important you get that. Now, in this spectrum, if you're nonpolar, okay, bond, your H2, your F2, it's the same element bonded to themselves, having the same electronegativity, so therefore you're going to be sharing electrons equally. So all of these guys are sharing electrons equally, something you must know. Okay? So share electrons equally. Share equally. Now everybody else is going to have from 0 to 1.7 unequal sharing because you have 2 different electronegativities, and this is what we call a polar covalent bond. Okay, why polar covalent bond? Well, let's look at hydrochloric acid. Hydrogen has 1 valence electron, chlorine has 7, and notice I'm writing the electrons closer to the chlorine to show that the chlorine, being more electronegative than the hydrogen, is pulling that pair closer to the chlorine. So the side of the chlorine, so this side of the chlorine bond is a little bit negative, and the side of the hydrogen bond is a little bit positive because it kind of had electrons pulled away. So polar covalent bonds are unequal sharing because they have different electronegativities. Nonpolar bonds are equal sharing because they have the same electronegativity. Now I could ask you, who's more polar bond? Who has a more polar bond? So as the difference in electronegativity increases, case in point HF, here's 2.2, and here's fluorine, which is 4.0, the most electronegative atom. You can see that difference is greater. So as we move across this little graph here and we get the difference is greater, we become more and more polar. The polarity increases until eventually, you got it, we become ionic. All right, very important. Now what I've been drawing here is Lewis dot diagrams. Okay, and we're sharing electrons to get that magical 8 number, which is called the Octet Rule, to fill the second energy level. Look at water. Water has 1, 2, 3, 4, 5, 6 valence electrons. And I should say oxygen has 6 valence electrons. It's in group 16. It's 2-6. There's your 6 electrons outside of a filled energy level. So it can bond with 2 water molecules. Now water has 1 valence electron. All right, and there is the Lewis dot diagram, okay, for the bonding of water. Now notice it's bent because these lone pairs, okay, repel these pairs downward, and this is a bent shape. Okay, now the shape of a molecule determines the polarity of the molecule. We have been just talking about polar and nonpolar bonds. It's important you understand the difference. Bonds. Now I'm going to talk about polar, nonpolar molecules. There's a difference. The bond is very simple. Between the same nonmetals, there has to be nonpolar bonds. Between different nonmetals, there has to be polar bonds. Why? Sharing unequally creates these charges. Sharing, let's do that again. So when you're nonpolar, okay, you are sharing equally, like these examples, and when you're polar, you're sharing unequally, like this example here. Okay? All right, too many arrows. All right, now, if I want to talk about the molecule, what I'm really talking about is, hey, one side has less electrons than another. We have an unequal distribution of charge. So this would be a polar molecule. I've got a lot more electrons over here, so it's a little bit negative, a little bit positive. Okay, how'd that occur? Because of what? Polar bond. So to be a polar molecule, you have to have, number one, a polar bond. 2 different nonmetals. Okay, and the second thing you have to have is you have to have asymmetry. Asymmetry means that you do not have the same stuff all the way around. It means your polar bonds, okay, cannot cancel out. For instance, if you look at methane, 1 carbon meth for those that took organic already, okay, 1, 2, 3, 4 valence electrons, okay, and each hydrogen has 1, so carbon has its magical 8. Now, this is 4 polar bonds according to the Regents, 2 different nonmetals. Now, because the shape is the same all the way around, these 4 polar bonds cancel out, and we would say that this is a symmetrical molecule, meaning there's an evenness even with the unsharing in all directions. So we would say it would all cancel out, and this would be a face, but it also would be, okay, meant to be a parentheses or something, meant to be, this is a nonpolar molecule, right? Nonpolar molecule because of its symmetry with polar bonds. Okay, and this shape is a tetrahedral. You're responsible for that shape. Okay, tetra for 4 sides. Now, water has polar bonds, 2 of them, but because it's asymmetrical, It's a polar molecule. Why is it polar? It's got a negative side and a positive side. If I was to draw this molecule, kind of bent kind of thing, there's going to be more negatives in the oxygen end than in this end. So we would say that this side of the molecule is positive and this side of the molecule is negative. Okay, but we can't do that with methane. If I was to draw a circle for methane over here, okay, they're even in all directions. Here it's not even because of the asymmetrical shape. So very simple. To be a polar molecule, you have to be asymmetrical with a polar bond. Let's go through some examples. Okay, look at carbon dioxide. You should know carbon dioxide looks like this. Double bonds. Notice there's no lone pairs to bend it downward. So this is a linear molecule. Okay, it's linear, and even though it has polar bonds, two different nonmetals, so this is definitely polar bonds in this molecule, because the shape is symmetrical, same on both sides, these polar bonds cancel out. So this is a nonpolar molecule with polar bonds. Okay, look at ammonia, another example that pops up. Now I'm going to draw dashes. Dashes represent a pair of electrons. Okay, ammonia has what? Has polar bonds, two different nonmetals. Is it symmetrical? No, it's not the same all the way around. So this is a polar molecule. It has polar bonds and is asymmetrical polar molecule. Okay, and if you need more work on this, please click on my videos below. I work on this extensively. Okay, you have to understand these. All right, so what are the properties of covalent compounds? Well, covalent compounds are called molecular because they make molecules, and their formulas are molecular. Molecular formulas are exactly how they exist in nature. Hydrogen peroxide exists as H2O2. Its Lewis dot diagram looks like this. The eyeglass exactly exists. This is the molecular formula. It's empirical, right? What's the empirical? Empirical is the lowest ratio, and that would be HO. Ho! Okay? So here's the molecular, how it exists in nature. Now, fancy word for molecular compounds is covalent compounds. Anything that is covalent makes exact particles like this. They do not make crystals, okay, for the most part. Okay, so here molecular compound, you're thinking covalent. Okay, what are the properties? Well, because they hold electrons tightly, they're brittle. They're easy to break apart. Okay, like the OCD, they're not flexible. Okay. So think about dry rotting of a leather, think of racquetball shattering, okay, think about a vase cracking, think about pottery, plates, all those things, okay? So they're brittle solids. They're terrible conductors. They're so terrible at conducting, they're good insulators. Why are they good insulators? Because their electrons don't move so well, as we talked about. So all the properties we've talked about in nonmetals is the same properties we have for molecular compounds. Their melting points and boiling points are low. They have weak attractive forces of themselves. By the way, these are basically the same properties as organic compounds, as we've learned about in this year. Organic compounds is based on carbon, hello, a nonmetal. So molecular, okay, nonmetals, all the properties we've learned tend to be insoluble for the most part. Certainly there are examples of molecular compounds being soluble, all right? And if anything else, remember water is definitely polar. Okay, it's got that lone pair bending it down like these do. The CO2 I drew above, okay, doesn't have a lone pair to bend it down, so that's why it stays linear. All right, so those are the basics of the bonding. Now there's one more type of bond, and that is metallic. And metallic bonding is the bonding between metals. Okay, so if you've got copper solid, iron solid, iron atoms bonding to iron atoms, or copper atoms bonding to copper atoms, will have this chemical formula. And what metallic bonding is that you have this sea of mobile electrons that are able to pretty much migrate throughout the entire substance. They're attracted to these nuclei, but not so much to stay in one direction, so they're able to move throughout the entire structure, and this gives them great properties of electrical conductivity and thermal conductivity because electrons can move. Okay, so it's important you understand the catchphrase is C of mobile electrons. Please, if you don't get any of this, look at the other instructional videos that go in detail. So this covers essentially the bonding unit.